not only can we revolve regions around the x-axis, they can also be revolved around the y-axis. That's the situation that's going on with example 12. We see that we have function y equals 2 root x, the y-axis and the line y equals 2 serving as the bounds. So we get this blue region right there. But this time we're revolving it around the y-axis. All right? So we're actually getting the tornado that was on its side in the previous example. Now we actually get the tornado. If we're going to go around the y-axis, there's a couple of choices, but if you're using the disk method, which I'm going to do in this case, all right, we still have a whole bunch of cylinders, and we have to add up those volumes of those cylinders. But things are a little bit different this time because the cylinders are no longer vertical, they're now horizontal. So the height of the cylinder is no longer a little bit of the x-axis, it's a little bit of the y-axis. So our differential is a dy. So when we're doing our integral, we cannot have pi times the integral from a to b of f of x squared dx. In fact, we need the dy, right, in order to have the height of our cylinders. So this is out. Because if we're going to have y as our differential variable, all the variables need to be in terms of y. So that means our integrand can't be a function of x being squared, it needs to be a function of y being squared. Now pi is a constant, so that doesn't need any change at all. But the other thing that needs to be changed are the bounds. Because before, we were interested in the x, the range in the x. Now we're interested in the range of the y. Because remember, we have a whole bunch of cylinders being stacked on top of each other. They start at y equals a number, and they finish at y equals a number. So while we still have numbers up here as our bounds, they're actually in terms of y instead of terms of x. All right, up here, this is x equals a and x equals b. But now we have y equals. So quite often the notation is to use the next two letters in the alphabet of C and D. Right? Now we don't need to have the y equals there. There's nothing wrong with putting them in. But this is very similar to what I've crossed out. But it's actually the situation that we need. It's our disk method for this problem. So let's go ahead and do that. First of all, we need the function to be in terms of y. All right. So we have y equals 2 root x. We need this to be x equals. All right. So what do? We know a little bit of algebra here. We'll divide by 2. So root x is equal to y over 2. And that means that x is equal to y over 2, that quantity squared, or y squared over 4. So when we make our integral, pi is out front, and our integrand will be that y squared over 4. Now, this needs to be squared, so we're going to wrap that and square it. dy is our differential, and then it's a matter of what are our bounds. Well, we're starting at the origin, and we're ending up here, which is at the horizontal line y equals 2. So once again, our bounds will be from 0 to 2. We have to solve this just like we did in the previous example. We need to simplify our integrand just a little bit before we take the antiderivative. So we have y squared being squared and 4 being squared. So it looks like we can actually can I just erase this real quick and make it, actually erase the parentheses as well, y to the 4th over 16. All right, y squared is y to the 4th, 4 squared, 16. And this 16 is actually a constant. All right, we're dividing by 16 or multiplying by 1 over 16. Since it's a constant or coefficient, we can pull that out front, leaving us with just the y to the 4th. That's a much easier antiderivative to take. We've got our pi over 16, and then this becomes y to the 5th over 5, and that's being evaluated from 0 to 2. We plug in 2. Once again, we have the 2 to the 5th, or 32, over 5. And then we also have the pi over 16. So we're looking at 32 pi, and then 5 times 16 would be 80. So that's an unsimplified answer. We also, the 32 could cross out with the 16 and leave us with a 2 up top. So 2 pi over 5 would also be a perfectly fine answer.